Unit 3, Section 4, Graphing Polynomials. The steps to graph a polynomial: we need to find the y-intercept, we need to find the x-intercepts and their multiplicities, determine the end behavior, plot all of that info, and then draw a polynomial curve between the intercepts. So real quick, the behavior at the x-intercepts: if the multiplicity is odd, the graph crosses the x-axis. If the multiplicity of the x-intercept is even, f of x does not cross the x-axis. It'll touch and return the same direction. The end behavior of a polynomial is determined by the leading coefficient, if it's positive or negative, and the degree of the polynomial. If the leading coefficient is positive and the degree is even, the end behavior of the polynomial rises left and rises right. You can think about x squared has the same end behavior as x squared. And if the leading coefficient is negative and the degree is even, the polynomial has the same end behavior as negative x squared, which would be falls left and falls right. With a leading coefficient positive and degree odd, the end behavior falls left and rises right, which is similar to x cubed. With the leading coefficient negative and degree odd, the end behavior rises left and falls right, which is the same end behavior as negative x cubed. So if you can remember those basic functions, that can help you with end behavior. And then real quick, let's just remember to find a y-intercept, we always compute f of 0. And to find x-intercepts of a function, you set the function equal to 0 and solve for x. The intermediate value theorem says that if we have 2 points on the graph and they have opposite signs, there has to be at least one path to get from one point to the next that crosses the x-intercept. So all we know is that there has to be at least one. There could be more than one because it could do something like that. So if y1 and y2 have the same sign, so let's say that they were on the same side of the x-axis, it cannot be determined that an x-intercept has to exist. It's possible to get from one point to the next without crossing the x-axis, but it is also possible to cross the x-axis again. So it is not conclusive if y1 and y2 have the same sign. Okay, let's graph negative x times x minus 1 squared times x plus 2. First, we're going to find the y-intercept. Plug in 0. This one's really easy because with the factor of x out front, f of 0 is just 0, so the origin is on the graph. Now, to find the x-intercepts, we set the entire function equal to 0 and solve. And the zero factor property says that if any factor is 0, then the entire equation is equal to 0. So set each factor equal to 0 and solve. With the x minus 1, the quantity squared, we need to note that x equals 1 is a 0, but it has multiplicity 2. And so our x-intercepts as ordered pairs are 0, 0, 1, 0, and negative 2, 0. And keep in mind that x equals 1 has multiplicity 2. And that's going to change the behavior at the x-intercept. Then the leading coefficient is negative, and the polynomial is degree 4. So if you add up the exponents, you would have a negative x to the 4th if that were multiplied out. So the end behavior falls left and falls right. So when you graph this, you put the end behavior on the graph. You put the intercepts, in this case the origin, so that's an x-intercept and a y-intercept. And then you have to draw the curve through them. At negative 2, the graph crosses because of odd multiplicity. At 0, the graph crosses because of odd multiplicity. And then at 1, the graph touches that x-intercept and returns the same direction because of even multiplicity. Okay, on this next one, we're going to use the graph to give the least degree polynomial. So we want to note that f of 0 is -6, and x equals -1 is a 0. With even multiplicity, since the graph touches and returns the same direction, which means that the factor would be x plus 1, and the least degree would be squared. X equals 3 is a 0 with odd multiplicity since the graph crosses. So the factor is x minus 3, and we'll leave that to the first power unless we need to adjust that to the third power, but there's a good chance, since this is asking for the least degree polynomial, x minus 3 to the first. The other thing is, and you can't necessarily just trust your eyeballs on a graph, but if this were cubed, the graph would inflect through that x-intercept, but it crosses straight through that x-intercept. Again, we're not going to necessarily trust our eyes on that. We'll let the algebra play itself out here. And the end behavior is falls left and rises right, so we have a positive leading coefficient with an odd degree. And there's 2 turning points, which means that the degree has to be greater than or equal to 3. Okay, and then here's how we actually solve this. So we take the x-intercepts and write their corresponding factors, but we need a leading coefficient out front because that might help us with the y-intercept. So x plus 1, the quantity squared, that comes from that x-intercept. X minus 3, that comes from that x-intercept and its behavior. And then when we plug in f of 0, we get, we know that f of 0 is -6. So 0 plus 1, the quantity squared, times -3. Now we have this leading coefficient. We would have -3a. We know that that has to be -6, so therefore the leading coefficient has to be 2. And all of the other information matches up. So the answer is f of x equals 2 times x plus 1, the quantity squared, times x minus 3.